the last thing that we were talking about on Monday was homeostatic imbalances of the heart, and one of those was congestive heart failure. And so the one example that I gave you, and it was in the video, was this idea that you could have a person that has their left ventricle not sufficiently pumping the blood. They pump the left ventricular assist, and the one that they had in the video was more like that, was more round. But this all goes up into the thoracic cavity, right? And so this actually does the work of the left ventricle. So when we talk about congestive heart failure, this congestion has to do with the blood kind of staying in the body when it's not supposed to. And so when we look at, so I'll write down, might have congestive heart failure already. Okay, so if the left side fails, so that is the side that is taking the blood that is going out from the oxygenated blood going out to the body. But what happens when the left side fails is you get what is referred to as pulmonary congestion. And what that means is that blood backs up into the lungs. Because it is not being pumped out fast enough, because remember, the blood coming from the lungs has to go to the left atria and the left ventricle. So the blood stays too long in the lungs, and what tends to happen is you get fluid developing in the lungs, and this can actually lead to suffocation. So fluid in lungs, and this can kill a person by suffocation, because the lungs are not able to get enough oxygen and get rid of enough CO2 because there's a buildup of fluid in the lungs. And so if we look at how this would happen, okay, so here are the capillaries that are surrounding. We haven't talked about the lungs yet, but the lungs have these air spaces which are called alveoli. And if there's pressure back onto the lungs, then the capillaries have too much blood, and what will happen is that fluid will be forced out of the capillaries and into the lungs. And so you have to treat this, right? And ultimately it could be treated with a heart transplant, right? Or it could be treated with drugs. It could also be treated by putting in the pump, right? The left ventricular assist pump. So the other problem comes if it's the right side. So if we look at the right side, then it's blood that is leaving the right ventricle. And so what happens if it's the right side, and it can be both actually, but what you get is peripheral congestion. And then you get fluid buildup in the tissues. And this can lead to edema. So this is swelling, and particularly it tends to be in the lower limbs, like in your feet and in the ankles specifically, and maybe even sometimes in the fingers you get edema, swelling, if the right side is not able to pump out the blood to the lungs, and it backs up into the body. Now, congestive heart failure can be caused by a variety of things, but one of the things that it can be caused by is something that we've talked about. Okay, so it can be caused by multiple heart attacks. So sometimes heart attacks are small and they start to just weaken the heart. And then sometimes you get the ventricles becoming really thin-walled and almost they become dilated. And that is called, let me see if I can remember what that's called. That is called dilated myocardiopathy. So dilated myocardiopathy. cardiopathy, I think it's opathy. Yeah. Okay, and so this is where the walls of the heart become thin and weak. Okay. It can also be due to, and these are all kind of related, but it could be due to atherosclerosis, which we're going to talk about is also related to hypertension. So hypertension is high blood pressure for prolonged periods of time. So your blood pressure obviously fluctuates, but if you have chronic hypertension, then your blood pressure stays high, and that could damage the blood vessels. It can also ultimately lead to death of the heart tissue because it's not getting enough oxygen. Okay. So also when we look at homeostatic imbalances of the heart, we can talk about regulation of heart rate. Okay, so what is it called when your heart rate is chronically high? So it's like always too high. Does anybody know? What? It's too high? So it starts with a T. Tachycardia, right? So tachycardia is that it's too high. That's with a Y. Okay. And generally this is like sustained over 100. So 100 beats per minute, right? But it can be really high. So I've known people that like their heart rate is like 200, right? And they go to the hospital and they give them drugs to try to lower their heart rate back down. Sometimes tachycardia can be brought on by stress, because remember your stress hormone, your adrenal glands can release epinephrine or adrenaline, and that can cause a spike. Sometimes diet can also influence heart rate, and anxiety can also be a source of chronically high heart rate. One of the reasons why they were really concerned about high heart rate is not only does it, kind of stress the heart, but it can lead to fibrillations. So it can lead to AFib, for example. If you have high heart rate, then your atria could not stop contracting properly, and then that could cause fibrillation. Okay, so the opposite of tachycardia is bradycardia. Right, so this is a low heart rate. And this can be a problem. Some people who are on drugs for high heart rate, they're on what are called beta blockers, and we'll talk more about that when we get to the endocrine system. They sometimes have low heart rate, so that even like climbing a set of stairs becomes difficult for them because they're on drugs that suppress their heart rate, and so they constantly have to rest, right? So they cannot exert themselves oftentimes as much as they would like to. So this tends to be lower than 60 beats per minute. Now, bradycardia can actually be a good thing if it is due to exercise. So when we look at aerobic exercise, something interesting happens. One of the things that happens is the heart gets bigger. And so what this means is that this increases the amount of blood that the heart can contract and propel out. So this increases the stroke volume. So what tends to happen when people are like long distance runners or any kind of aerobic athlete is that their heart rate tends to decrease. So they have a decrease in heart rate. Right? So long distance runners might have a heart rate resting heart rate that's more like 40 beats per minute, right, rather than 60 beats per minute. And that's just because their heart is more efficient. Okay. So last thing I just want to mention just a little bit is the development of the heart. So in each of the chapters of the systems, they talk about embryonic development of the different structures, and the heart is actually one of the very first systems that comes online during embryonic development. And it's a really interesting pathway to development because it actually kind of starts out looking very similar to the heart of a fish. So you see that blood kind of comes in one direction, and then we have this one ventricle that then would pump blood out, right? But remember that during our embryonic development, we develop from a 2-chambered heart to a 4-chambered heart, and so it has to do with kind of the folding in or back on itself. And so you can see that it kind of bends, and then we get the development of the 2 ventricles and the 2 atria. Okay. So when we look at the fetal heart, there's a couple of things you need to know about fetal circulation. So when we look at the fetal heart, we see that blood bypasses the lungs. Okay, so it bypasses the pulmonary circuit. And the reason is that, well, one, there's fluid in the lungs, and 2, that they're not using their lungs to get oxygen. So remember that they're relying upon the mother's body. The mother gets oxygen, and then she passes the oxygen to the offspring across the placenta. And so they bypass the lungs. And so we have a couple of shunts that include the foramen ovale. And you probably looked at this last week in lab. But this is an opening between the 2 atria. Okay. And it actually has a flap that closes upon birth. So blood that's coming in is unoxygenated and it's going to the right atria, but then it bypasses the right ventricle entirely, and it goes to the left atria, left ventricle, and then back out to the body and back out to the placenta. Okay. So sometimes you'll hear people say, oh, well, the baby was born and had a hole in its heart, and sometimes it's this. So sometimes that flap does not completely seal over, and so sometimes they have to go in. Hopefully it might eventually seal over, but sometimes they have to go in and they have to surgically correct that, okay? So that's the foramen ovale. And then we have another shunt, which is called the ductus arteriosus. And the ductus arteriosus connects, so it's a shunt between the pulmonary trunk and the aorta. So some blood will make it into the right ventricle, and if it goes out to the pulmonary trunk, most of that blood gets then shunted to the aorta, and it goes out and it bypasses the pulmonary system entirely and goes back to the systemic system. So in your book, there's a diagram that shows this early, or the development of the fetal heart. Can't tell if it's actually, oh, there we go. Okay, so this is a diagram, and so the foramen ovale, we can actually see that in us. It just is a kind of an indentation, right? It's a little thinner wall, part of between the 2 atria. And then the ductus arteriosus, so this would be the pulmonary trunk, and so this would shunt blood out to the aorta and then out to the body. Okay. So there are some other birth defects that you can see in hearts, and you don't need to know the name of them, but some of these include an incomplete separation of the ventricles. So if we look at the ventricles, remember that they start out as one ventricle, and then you have to develop a wall between them. Okay. And so here you can see that there's actually a hole in between the ventricles. And so that would be really a bad thing to have, because what that means is that you mix oxygenated and deoxygenated blood together, and so the baby would not be able to get enough oxygenated blood. And then sometimes you can also have narrowed aortas, which cause congestion in the heart, because the heart has to pump too hard to get the blood out, and so the blood kind of backflows into the heart. And sometimes you get multiple problems with the heart. And so notice that that's actually that, some of them are really quite common, right? Heart defects that we see in babies. And so this is a common thing that babies have to have surgery upon birth if their hearts haven't completely developed properly.
How do they fix that, like the pressure? How do they put in there to
I don't know what they put in there. It might be something that's synthetic. It's just probably something synthetic. They fill it up. Yeah. Okay. Okay, so we are going to start on chapter 19, which has to do with blood vessels. And so if we look at the structure of the blood vessels, we need to remember that blood vessels are organs. These are organs, and they're organs because they contain multiple types of tissue. So they contain not only epithelial tissue, but they contain muscular tissue, they can contain connective tissue, and nervous tissue. So they're considered organs. And so when we look at the blood vessels, there are 3 different layers. And these layers are called tunics. And the innermost layer is called the tunica intima. So think that this is the layer that's closest to the lumen. So a lumen is just the space where the blood flows. So this is epithelial tissue. And it's called the endothelium. And this really needs to be smooth, because if you get rough, remember that one of the things that happens is that the platelets like to cling to the sides of damaged blood vessels, and then you get blood clotting, and then that could be due to infection. So like any infection that you get into the circulatory system that could cause inflammation can be bad, because it can cause blood clotting, and then it could maybe even lead to atherosclerosis, which is plaque buildup. And so this needs to be smooth. To prevent clot formation. Okay. So the middle one is media. So it's tunica media. So just think middle. And this is the one that contains the smooth muscle. It also has elastic connective tissue. And this is really important, because we do not want our arteries specifically to become hardened so that they don't respond to the change in blood pressure. And so we want it to bounce back. So the blood vessels expand, but then we want them to go back. We don't want them to remain dilated, and we don't want them to get hard so that they don't expand, because that could affect blood pressure as well. Okay. So the elastic tissue, so they expand and contract. So I'll just put expand and bounce back. Okay. Okay. Then we have the tunica externa. And this contains connective tissue. So it has lots of collagen fibers. So it helps to protect the blood vessel, right, from rupturing. But this is also where we have nerves supplying the blood vessels. So we have nervous tissue. And one of the really interesting things about our blood vessels is that they are only innervated by the sympathetic nervous system. So I'll put only innervated by sympathetic nervous system. So that's the fight or flight. Oops, nervous system. And they actually, the sympathetic nervous system actually keeps the blood vessels under a constant state of partial contraction. So the blood vessels, the smooth muscle is never just completely relaxed, right? So this keeps the blood vessel, and it's called tone, sympathetic tone. So it keeps the blood vessels under constant contraction, state of contraction, okay? So this is what is called sympathetic tone. Okay. There's also lymphatic vessels, and there's also circulatory vessels. So lymphatic and circulatory vessels are in this external tunic. So even some of the larger blood vessels actually have to have their own blood supply, right? So like the brachial artery has its own blood supply, right? And because it has to get oxygen and nutrients so that it can maintain homeostasis and can cause, and the smooth muscle needs oxygen and nutrients to contract, okay? So if we look at the diagram of these different layers, okay, this is a diagram that shows in the arteries, let's look at it in the artery. So the tunica intima is just this, the very most thin layer on the inside. Okay. The tunica media is the smooth muscle, so this would be a good diagram to have on a test, right? And then the elastic looks like, in the arteries here, it looks like Swiss cheese, right? So those are elastic fibers. And then this outer connective tissue is white because it's full of collagen fibers. You can see the yellow in it would be nerves, sympathetic nerves. And then you can see that there's a blood supply to the blood vessel itself. And you can see that there's a difference, and we'll talk about the difference between arteries and veins in a second. Okay, so let's look at arteries. Okay, so arteries carry blood away from the heart. And because of this, they're carrying blood at higher pressure. So arteries have more smooth muscle than veins. And what the smooth muscle allows them to do is to constrict or to dilate. And these are referred to as vasoconstriction and vasodilation. So if we look at vasoconstriction, this means that you're decreasing the diameter of the blood vessel. And this is going to increase the pressure. So what tends to happen is if you constrict a blood vessel, it will shunt blood to a different location in the body. So if we're shunting blood away from the skin because we're cold, we would vasoconstrict the blood vessels that carry blood to the skin. Okay. The next one would be vasodilation, where we would increase the diameter. and hence we would decrease the pressure. And so this means that blood tends to be shunted towards where we open up the blood vessels, because blood wants to travel in the path of its least resistance. So it will tend to travel towards blood vessels that have become dilated and open. So this would be shunting away from and shunting towards. Okay. So there's actually 3 different categories of arteries. One is that we have elastic arteries. So put 3 categories. First one is elastic. These are the large arteries near the heart. And so because they're called elastic, they have more elastic tissue. And so they actually function to smooth out the blood flow. So if the blood causes them to constrict, then they'll push back on it, and it actually helps to propel the blood forward. So it smooths out blood flow. And this is important because it helps to protect blood vessels that are down the line from the elastic ones, so that they do not experience like really high blood pressure and then no blood pressure. So the pulse, you know, the pulsing of it. And so it kind of protects them from rupturing. Okay. So that's the elastic blood vessels. We then have the muscular arteries. And these are the ones that you will need to learn. So these are the ones that shunt the blood to different organs. I'll just put different regions because it could be down to the arm. Okay, and so I'm going to give you, actually I should have handed this out ahead of time. I'm giving you all the circulatory vessels that you need to know for the lab practical and the final exam. So this will eventually go into your lab notebook. And you can work on this before lab. If you're not going to be in lab, you can do it. Okay, and put it in your lab notebook for points. Okay. So what I want is just a general description of the vessel, like maybe where it is, where is it going, right? And these include arteries as well as veins. And so you need to label them on the sheets, right? And you need to figure out which sheet, because they're not color coded. You need to figure out which sheet would be red and which sheet would be, oh, actually I wrote them there. So the first one would be red. And I know that this is arterial if I was looking at it and it wasn't red, because I can see the aortic arch, right? So I can see, and then on this one that's blue, there's no aortic arch, right? There's just that inferior and superior vena cava coming into the heart. Okay. So this will go into your lab notebook. You don't have to have it due, ready until when you turn your lab notebook in at the very end, but it'll help you when you're studying for the midterm exam. Okay. So the ones that are on here are primarily the muscular arteries, like the brachial artery or the femoral artery. Okay. Okay. Then we have what are called arterioles. And these are very small arteries. And these deliver blood to the capillaries. So arteries start out big and they branch and branch and branch into smaller vessels until we get arterioles, and then they go to capillaries. And then veins are exactly the opposite. Veins converge. So they start out small and then they converge into bigger and bigger blood vessels until we get back to the heart, right? Okay, so in your book, there is a diagram that shows this. So this is my elastic arteries, right? Way close up to the heart, like my aorta, my brachiocephalic trunk, that kind of stuff. And then muscular arteries then distribute the blood, and they are muscular because they contract, they vasoconstrict and vasorelax. And then we get down here to the arterioles, which then can branch into the capillaries. And we're going to talk about capillary exchange in a little bit. There are some connections between blood vessels that allow blood to be shunted away from capillaries. And these are called anastomosis. And so anastomos is a connection between that bypasses the capillaries, okay? So you want to write that down. An anastomosis is a vessel that connects an artery and a vein bypassing the capillary bed. Right. So if you're shunting blood away from the digestive system, for example, into the muscles during the fight or flight reaction, that would be an example of that. Okay, so let's look at the veins. So we're still talking about blood vessels. The veins obviously carry blood toward the heart. It's usually unoxygenated. Right? They have less smooth muscle because they generally do not constrict or dilate. But what they have instead is they have valves. And so valves help to prevent backflow of blood. The other thing about the veins is that they tend to be associated with skeletal muscle. So just put associated with skeletal muscle. And so what that means is that as you move, it tends to put pressure on the veins and help to move the blood up against gravity. So movement in the body helps blood flow in the veins. So you probably have all experienced this phenomena of standing in one place for a long period of time, and your feet will start to kind of swell and they'll start to get red and they'll get itchy, right? And that has to do with that the blood is starting to pool in your extremities. And so you need to move in order to keep the blood flowing, right? There's also some people that have problems with their blood vessels in their legs, sometimes wear what are referred to as compression stockings. And a compression stocking will actually put a certain pound of per inch pressure on your leg, for example, and that will help to keep the veins under a constant state of contraction, partial contraction, and that tends to help to move the blood back out of the appendages. Does anybody know anybody that has to wear compression stockings? Yeah. Is it genetic? Is it work related?
She's had lots of issues with the
right. Generally what happens is that you can get what is referred to as varicose veins. And this is where you have damage to the blood vessels, specifically the veins, right? And it causes them to bulge. And so one thing that they do sometimes is they actually go in and remove these veins. And then after you have them removed, generally you wear the special socks that help to compress and move the blood back up. And so in your, they don't have a picture in your book, but I found one online that shows the valves. So here's the skeletal muscle, right? And here's the valves. And the valves are such that once the blood moves up to a certain point, even if it flows back, it will close the valve. And so it's the backflow of the blood in the veins that actually closes the blood or the valve and keeps it moving in one direction. Oops. So this would be a person that has varicose veins. And so what has happened is that you get damage to the valves, and then the blood just starts to kind of accumulate there, and it causes problems with their circulation. And so people go in, and I think they call it stripping. So they go in and they'll just strip those right away. This tends to be, there's part genetic and then part environmental. Tends to happen a lot of the times also when if you're a pregnant female, because you have so much blood and there's so much pressure against your veins that sometimes being pregnant can lead to varicose veins. Okay. So if we look at the amount of blood and where it is in the body, you'll see that most of the blood, 60% of it, is actually found in the veins. And that is because it's under low pressure. So underneath that veins, you want to write low pressure, and you want to write 60% of the blood is found in the veins at any given point in time. So the trick is getting that blood to move back up fast enough so they can go back to the heart and back out to the lungs and back to the body. Okay, so let's look at capillaries. So capillaries are thin-walled. They lack smooth muscle. So they themselves cannot constrict, but they have precapillary sphincters associated with them. So the precapillary sphincter is smooth muscle. Right, so this is smooth muscle that can shut blood off to that particular region. So can prevent blood from flowing into the capillary bed. And a sphincter is a round muscle, and so it's kind of like prevent blood from flowing. Oops, flowing, sorry, flowing into capillary bed. Okay. So the important thing to realize here is that this is where gas and nutrient exchange takes place. So it does not occur in the arteries, it does not occur in the veins, it only occurs in the capillaries. So this is where we have blood exchanging with interstitial fluid. Right? So blood delivers oxygen and nutrients like glucose. Right? And then going the other way, this other arrow would be carbon dioxide. It picks up carbon dioxide and wastes, including urea, which is a waste product from the breakdown of proteins, for example. That's our nitrogenous waste that we pick up. Okay, so this is where we have exchange. Does not occur anyplace else. So we have different types of capillaries in different locations. Most of the types of capillaries that we see, so there's actually 3 types. Okay. Most of the types that we see are what are called continuous. So like this would be most common in the body. So this would be like in the skin and in the muscles, etc. Right? And this is actually the least permeable. So this actually prevents the least exchange. So some of the capillaries, like when we're talking about the capillaries in the kidney, are actually have bigger holes, right? So because these are continuous, it means that there's not a lot of space between the cells. And so these are the least permeable of all the capillaries. Okay, so the most common but least permeable. Then we have what is called the fenestrated. And fenestrations mean holes. So this has holes. And this can allow large molecules to kind of come in, or come out of the capillaries. And it can also kind of allow a little bit for the movement of cells. So this is associated with the kidney, which would be filtration. And in the small intestine, and this would be absorption. So absorption of nutrients and filtration of blood. That's where we would have fenestrated capillaries. So these are more permeable than the continuous. Okay. So if we look at a diagram that shows a picture of these, okay. So continuous means that the cells are pretty close together, right? And so here you can see it's very thin. There's no smooth muscle. There's a little bit, there's epithelial tissue, the endothelial, and you can see that there's like little spaces. And sometimes the blood vessels can become very leaky, like when you're having an allergic reaction. The blood vessels will dilate and they'll become leaky due to the presence of histamine, and your tissues will swell because fluid moves out through them. Okay, so that's the continuous. Notice that the red blood cells just flow single blood cell through. It's very tiny. Have this down at the bottom. Oh, come on. Okay. So this is fenestrated, is up above actually. So this is the fenestrated. So those little holes in the cells, those are what the fenestrations are. So fenestrations are little holes or pores in the cell. Okay. And then the last kind are the sinusoidal. And they have big holes, big sinuses. And this would actually be the most permeable. And so if you look at where it's located in the liver, right? In the bone marrow, so the bone marrow would be where blood cells can enter into the circulation. So cells can actually move through those holes. And in the spleen, where the red blood cells are broken down and the platelets are stored, they can actually come out. So the red blood cells and the platelets might actually be able to squeeze out through the fenestrated capillaries. So this is not fenestrated, sinusoidal. So this would be the third one. Okay. And they are the most permeable. Okay. I don't know if there's, oh, I do want to talk about capillary beds. Okay, so coming in at the capillary bed is the small arteriole. And leaving the capillary bed is a very small vein called a venule. And so I'm not sure why they left the I out of venule, but that's how they spell it. Okay, so that's the correct spelling. So that's a really small vein, venule. Okay. Now, connecting the arteriole and the venule is like a major thoroughfare, which is called a meta-arteriole. So I'm just going to kind of branch this off. So this would like branch off, and then this would branch here, right? And then I'm just going to put a little major pathway, right? And this major pathway is called the meta-arteriole. Okay, so this is what is referred to as a thoroughfare. I don't know how to spell that. We'll just put pathway, that's better. Path that bypasses the capillary bed. So this is where the sphincters play a big role. So if the sphincter is relaxed and it's open, then the blood will flow into the capillary beds. If the precapillary sphincters are closed, then the blood flows through the meta-arterial. So in your book, they show a diagram that talks about that. Okay, so this right here would be the meta-arterial right here, right? And so you can see that these are where those precapillary sphincters are important, because if they're constricted, they shut that down. And so think about like when you run and blood, the capillaries in your skin open up and your blood in your face turns bright red, right, for thermoregulation. And think about when you're cold and your face turns pale, because the blood has been shunted and doesn't go flow into the capillaries. Okay, so I want to talk about the handout that I gave you. So the last part of the lecture will just be this. Okay, so this handout that I gave you, just the cardiac output review. I was hoping to get to blood pressure, but I didn't get to that. So, but I wanted to talk about it before we left. I handed them out at the very beginning. Okay, did everybody else get one? It's called the cardiac output review. Okay. So the idea here is to put a plus or a negative, whether or not something like this would cause cardiac output to increase or decrease. So I just want to write hypertension. That would be high blood pressure. You put that under high blood pressure. Hypotension would be low blood pressure. Okay. So what do you think about with hemorrhaging? What does hemorrhaging do to your blood volume? Decreases it. So how is it going to affect preload? Decrease, right? So then it would decrease the cardiac output. Okay, so I put a negative there. What about congestive heart failure? Decrease. And so that has to do with the stroke volume, right? If the heart is not able to contract, and so you might want to write down there, you know, that has to do with stroke volume. The heart is not able to contract strong enough in order to pump the blood up. So stimulation of the sympathetic nervous system. Increase, and how does it increase it? Due to what variable? Heart rate, yes. Okay, so that increases heart rate. Okay. Hypertension, what variable does that affect? Would be preload or afterload? Afterload, right? Because hypertension tends to be a problem in the arterial system and not the vein system. So hypertension would decrease cardiac output. Atherosclerosis, if you have a decrease in the diameter of the blood vessel, that also would increase blood pressure. So that would be also a decrease. Hypotension would be low blood pressure, right? And so the afterload would be less. And so that would actually increase. But then you have a problem is, are you getting blood back to the heart? So your preload. So that one would be like, I would put like a little question mark, because you would have decrease in preload. No, you have a decrease in preload, but also a decrease in afterload. Yeah.
Could you explain atherosclerosis?
Okay, so that has a plaque buildup in the wall of an artery, and so that is going to decrease the diameter. So that is going to increase the pressure. So if you have atherosclerosis in your major arteries, then that is going to increase afterload, and so it's going to be hard for the heart to pump it back out.
So would that be a problem?
Okay, so that's negative. Yeah, so the hypotension could be, it could have side effects on both ends. So I would actually put positive negative on hypotension. Okay. How about epinephrine? What kind of chemical is that? It's a hormone, but it's also a neurotransmitter, right? So it actually works both ways, but that would increase heart rate. Decrease in afterload with positive cardiac output. Increased contractility of the heart. That could actually also do to calcium levels. So that would increase. Relaxation tends to decrease. Stimulation of parasympathetic, what would that be? Decrease. How about increased preload? More blood returning to the heart. Increase. Exercise would increase cardiac output, but over the long run, it's actually maybe decreases heart rate, but then stroke volume increases. So I would just put that it increases cardiac output. So tachycardia, which is what? High heart rate, so that would increase cardiac output, and bradycardia is low heart rate, so that would decrease. Any questions about that? Okay, so I will hopefully see most of you on Friday, though some of you are going to be gone.
Page 27.